Hello, so in this problem, I have this rectangular coil that is rotating in a magnetic field, and it's rotating with a frequency f. The magnetic field here is uniform, so it doesn't change with position, and we are interested in finding the induced electromotive force as a function of time. We need to verify that it has this expression here. So E is equal to 2 pi f n a b times the magnetic field B times sine 2 pi f t. So, and of course, the setup that you see here, this is the principle of any alternating current generator. So we have this coil that is rotating in a large magnetic field, and this generates the electricity for household usage. So to find the value of the induced electromotive force, first we need to notice that what's changing here is not the value of the magnetic field and not the area of the loop, but actually the angle between them. Because and the flux, we know it depends on the angle. So we know that phi is equal to BA cosine theta. And here what is changing is theta. So here theta is changing the angle because we have this rotating loop. And to find the induced EMF, um, we know that this theta is going to be changing uniformly actually with time because we have this uniform rotation with a frequency f. So this theta is changing uniformly. So we can mention that theta is actually going to be equal to omega t, where omega is the angular velocity, and the angular velocity is equal to 2 pi f. Okay, and f here is the frequency of rotation that is mentioned over here. So this is the rotation, the frequency of rotation, and it's also required in the expression we want. So it's important to change this omega into 2 pi f. And if we now write the expression of phi, this is going to be BA cosine 2 pi ft. We notice that phi depends on time, so in order to find the induced EMF, we need to derive phi with respect to t. If we check for the derivative here, of course, now here we have n terms, so yes, I need to include n in this expression. So this is going to be n d by dt of BA cosine 2 pi f t. And if we want to derive with respect to time, we will notice that n, b, and a are independent of time. So all we have to derive here is cosine 2 pi f t. And this will give us the derivative of a cosine function. We have to write the derivative of the inside, okay, which is going to be 2 pi f, and multiply it by the derivative of cosine, which is sine. Actually, it's minus sine, 2 pi ft. So we get this expression for the induced electromotive force. Now, of course, the initial formula of the induced electromotive force will have a minus sign, and this will cancel out over here when we solve the derivative. So we got the expression that is actually required over here. Okay, and of course, this whole term here actually represents the magnitude of the electromotive force. So this whole thing can be written as E0, which is the magnitude or the maximum value of the induced electromotive force here, which depends on time, obviously. In part B, so I think there's a part B here somewhere. Okay, probably forgot to write it down. But in part B, we want to look for the value of NAB. It's over here. What value of NAB gives an EMF with E0 equal 150 volts when the loop is rotating at 60 revolutions per second in a uniform magnetic field of magnitude 0.5 Tesla? So let's write down the given. So in part B, we want the value of NAB. We are given that um, we are given that E0 is 150 volts. We are given that we are rotating at 60 revolutions per second. This is obviously F. We can know that from the unit, okay, which is revolutions per second. So this is the frequency. And B is given to be 0.5 Tesla. So all we have to do is write down the expression of E0, which is NBA 2 pi F. We are interested in the value of NAB. We know that AB is the area itself. Okay, so we can rearrange this. It will be E0 over the magnetic field B times 2 pi F. Okay, we know the value of E0 is 150, the magnetic field is 0.5, 2 pi, and F is 60. So this gives us the final value of NAB, which is 0.8 meters squared.